The broadcast is now starting. All attendees are in listen-only mode.
Hello, ladies and gentlemen. My name is Jeff Sloan, and I am the editor of Composites Technology and High Performance Composites magazines. Welcome to today's webinar titled High Temperature, High Density Epoxy-urethane Foam, an Economical Alternative for Soft Tools and Molds, presented by General Plastics. Today's presentation will be about 40 minutes long and will be followed by a brief question and answer session. If you have any questions during today's webinar, you may type them at any time in the question box in your GoToWebinar control panel. This webinar will be recorded, and a link to it will be provided to you via email soon after the conclusion of today's presentation. Our presenter today is Mitch Johnson, PhD, Senior Technical Director of General Plastics Manufacturing Company. In this role, he is instrumental in new product development and continually improving the performance of the company's advanced materials and processes. He is responsible for the company's R&D group and oversees a team of chemists and technicians and works with customers to create products that fulfill specific requirements and applications. Mitch joined General Plastics in 2008 from 3M Company as a product developer, where he created numerous coatings, protective materials, and foams. He earned his doctorate from the University of Utah, conducting his thesis work in the field of organic chemistry, and he pursued postdoctoral studies at Los Alamos National Laboratory, where he studied organometallic lanthanide chemistry. Please welcome Mitch Johnson.
Thank you, Jeff, and thank you all for taking time in your day to join me. Today we'll be talking about high temperature, high density epoxy urethane foam as an economical alternative for tools and molds. And the agenda run through today is telling you just briefly about who General Plastics is. Then we'll jump into looking at what soft tooling is versus hard tooling, and also what is HDU, and what are tooling board properties made with HDU, and some other applications for high density urethane. Then we'll talk about foam tool material selection, foam properties, and then cure profile considerations when looking at foam versus a metallic substrates. And then we'll do a case study with a hex tool. And then, of course, any questions towards the end. General Plastics has been in the Puget Sound region for its entire life, and we've been around for over 70 years. We started producing polyurethane foams back in the mid-50s, and aerospace is our key market segment, and that really expands from whether it's tools and molds for aerospace and other companies all the way through flyaway parts. We produce a number of temperature-ranged tooling boards and also a very large range of densities in those formulations. We have an on-site R&D staff and engineers to respond to customer inquiries and new projects, and to try to develop new products for the ever-growing market segments. And then also we have on-site analytical and testing capabilities, where we are able to do a fair amount of physical property testing as well as inspection on these parts and materials, and of course the ISO certifications and some other mil-spec certs as well. So just to get us all on the same page here, we'll go through some background info on, first we'll start with soft tooling versus hard tooling. So soft tooling is relatively low cost of material compared to some of the metallics. Very large density difference in the weight of the materials. Soft tools are very easily machined into complex shapes. Foam is really a very smooth, uniform, and a very fast material to machine through. Hard tools, metallics, you have to do some forming operations first, or if you're machining billet stock, it just takes more time and to machine out shapes. Soft tools can be easily modified. Because it's an organic substrate, you can use high temperature Bondo type materials to modify surfaces, or use hand surface techniques with cutting tools or sandpapers, grinders, to remove material to fit your final desired shape. And metallics, of course, more difficult to modify the surface after you've had a final shape. Soft tooling, however, is great for prototype, one-off, short-run parts. And metallics, they really find their value in high production rate parts in the automotive industry, a lot of consumer goods. So for soft tooling, you do have to compensate for larger thermal variances as you move from low temperature to high temperature cures. You must consider the CTEs. And of course, hard tools like in-bar alloys have virtually no CTE. Therefore, your calculations for very complex parts are a little bit more straightforward. Insulating materials. So looking at soft tools, you lay a composite up on top of a soft tool or foam tool. You're really only heating it from the oven exposed side of that composite. Whereas with a metallic tool and the thermal conductivity difference, you really do see heating and curing of your composite from both sides. Therefore, you're shorter cycle times. Tight tolerances are difficult to maintain at higher temperatures. That's really due to the thermal expansion coefficients of foam versus metallics. Like I mentioned, alloys like in-bar, you can maintain tight tolerances through large temperature ranges. Now, what is HDU? So, acronym stands for high density polyurethane foam, and that really is derived from a while back looking at alternatives to wood. And polyurethane, getting back to some real basics here, is a reaction product of isocyanates and polyols. In this case, could be amines, could be other materials like that. But you modify that thermal set plastic with blowing agents to alter the densities. And we consider HDU, the high density, to include densities above 12 pounds per cubic foot. The insulation industry, like the spray foamers, 2 pounds per cubic foot is what they call high density. So for the sake of discussion today, though, HDU is much more the high density materials from 12, and we make up to 50 pounds per cubic foot. And of course, urethanes, there's 2 basic processes to manufacture materials. One is a continuous process, which usually has set block sizes of width and thickness, or a batch process, which is much more customizable in your block sizes. So HDU tooling board specifically is extremely versatile applications. Because of the properties in chemistry are really infinite amount of combinations, we can really modify and change properties, toughness versus TG, thermal resistance, chemical resistance, and so there's really a boundless number of iterations that we can formulate to. So they're also highly solvent and chemical resistant. And that's important when you look at surface sealers that are solvent-borne, paints and coatings, and also even matrix resins for composites. They're resistant to vinyl esters, polyesters, of course epoxies and urethanes don't affect them either. It's also important looking at adhesives, what adhesives you can use on your substrate. And really, with varying degrees of adhesion, all the major types of adhesives work quite well with urethanes, whether it's a polyurethane or epoxy, or even super glue like tiny esters. Wide ranges of block sizes are also available. So with processes like a batch process, you can make very large blocks, 8 to 10 foot square, 2 foot thickness. So you have a large monolithic potential tool you can machine out of one piece. However, they are easily bonded together. So for handling purposes, most folks tend to buy smaller blocks of foam and then bond them up into their large structure on site. Foam is also easily machined and also easily sanded. So once your machining process is done and you want to, like I said, modify it or to create an even smoother finish, you can take a fine grit sandpaper and hand sand it down, or with a orbital sander. Dimensional stability, also very important, talking about tooling and fixtures. When we machine out parts of foam, you don't want it to move around on you, and that's also a very important criteria to discuss with your supplier. and also consistent density throughout the thickness. We'll talk a little bit later on how important density is to properties, especially when talking about autoclave type cures, where you have external pressure on the foam as it's heated up. And also swirls and large voids can pose problems as well. Tooling boards are now manufactured really free of these types of defects. And what swirls and voids, of course, just cause more handwork after your machining operation may reveal some defects. So applications for high-density urethane blocks, modeling and prototypes. The edge definition, fine cell structure are easily paintable. A lot of the automotive cars you may see at some shows are actually not clay, but they're actually polyurethane foam as a substrate. Mold making, which we'll talk about today more. Vacuum holding fixtures, so the picture to the right there is an actual vacuum holding fixture that the operator is inspecting. What that does is it basically holds, for non-metallics you can't use magnets to hold parts in place. So these actually can hold a part in place while you're either machining it or inspecting it. That goes into the next option, which is a QA check fixture. You can machine a part and use a QA check fixture to check the dimensional tolerances of your machine part. And also tool proofing. As I mentioned before, foam, especially in the lower densities, are much less expensive than metallic metal billet. And so we can check here and prove out your tooling programs on foam first before you commit to cutting into metal. So things to consider. These are all questions you should be asking yourself and discussing with your suppliers before you select a foam material for your soft tooling. What type of cure profile does your desired composite matrix resin require for curing? What types of pressures are going to be exhibited on the substrate? What's the exotherm of the resin expected to be? How many cure cycles must be performed? Is this a single cure prototype part, or is this a one you expect to get two pulls off of it, or 10 pulls? What's the desired surface finish? And that comes into a cost factor down the road. We'll talk about it in a minute. Also, how large is the tool? And then it goes in. That leads into the next question of: do you want to bond up your foam blocks before or after machining? You can use a smaller CNC and machine up smaller blocks and bond up afterwards, but that requires some additional planning as well. And what are the tolerances of the design? Are you able to machine after you cure your composite? All these questions should be considered prior to selecting a soft tooling material. Now, foam properties. They're very formulation dependent. Urethane foams are. Epoxy foams and hybrids thereof. Formulations really dictate what the coefficient of thermal expansion, that's the CTE, the glass transition temperature, strength and modulus, porosity, and of course density. And the glass transition temperature and CTE are two properties of the foam that really affect the engineers designing with the foam. And they're really heavily influenced by filler type and polymer cross-linking. And I mention that because a lot of the tech data out there is not all using the same ASTM method. And so it's really important to look at what the glass transition temperature and the CTE are over the temperature range that you're actually going to use the foam. So if you're doing an ambient cure, low temperature curing prepreg, you should be looking at CTE 60 degrees to 120 F. If you're doing a BMI resin cure, then the CTE and NTU should be considered all the way up to what the 350F, 375F cure is required. So within a resin system, higher densities will both increase modulus and strength and also reduce surface porosity. Of course, one thing I didn't list on there is the obvious one, that as you are increasing your density per cubic foot, the cost also goes up. So that's also where you get into surface finish requirements. If you desire a very fine surface finish, but you have a very large tool, perhaps you would like to use a lower density material and then use a filler and sealer system to create your fine surface finish. Those are all things to discuss with your supplier to make sure that when you order a foam material, that it shows up as you expect. So cure profile considerations. So of course, foam is much more insulative than metallics. Here I've picked 2 of our 18-pound per cubic foot materials. And just in general, we look at the room temperature data for compressive strength and modulus. They're really quite similar. Now, as you increase temperature, the 3718 starts to soften and weaken as it approaches its glass transition temperature at 250 F. Whereas the 4718, with a much higher glass transition temperature, is still quite a bit stronger, even to 350 F. So even though they're both 18-pound per cubic foot thermoset cellular plastics, the formulations are quite different. And the 4718 is an epoxy hybrid material that allows these higher glass transition temperatures and higher strengths. So as we move down through the tech data sheet, you'll see on the CTE, there's also a difference there as well. The lower CTE just helps reduce the amount of thermal compensation you need. Now, as the CTE is measured, that CTE that we report on our data sheets is from room temperature up to about 30 or 40 degrees below its glass transition temperature. Other test methods will report it from minus 20 F to plus 20 F. Now that not very useful for most tooling operations, and also depending on the type of filler used in the material can give you an artificially low CTE. Now when you heat these materials up, the test method is basically the substrate is saturated at that temperature. So what that means is as you're looking at the CTE value of 27 ppm, that 27 times 10 to the minus 6, that value is of the foam saturated over that temperature range. And we'll come back to that point in a minute because there are some correction factors that you need to use to get an effective CTE. And also, most of the foams that we make that are FR prefixed do pass fire safety, which is basically they will not support combustion once a flame has been removed. So cure profile considerations. Actually, go back to a little more about density as we move through that. The density is 4,700. At room temperature, the 18-pound versus 40-pound is almost a factor of 4 difference in compressive strengths. So as the temperature goes up and perhaps your curing pressure goes up, the higher the density will maintain its dimensional stability better. So as you increase the pressure or forces on that foam, the higher the density will be more resistant to any kind of deformation from external pressures or stresses. We also pay a price and cost for that higher pressure, higher density. But you can see the CTE is really the same for all 3 densities of material. And that's due to the resin system is identical for all those materials, so the resin will expand at the same rate. The only difference between these materials is just the amount of air or gas inside them. And these are all materials that do not outgas by measurements of the thermogravimetric analysis. So getting back to curing profiles and temperature considerations, from the Hex Tool M61 user guide from Hexcel, this is the recommended cure profile. And this is based off of a metallic substrate or a foam substrate if you don't wish to use a foam again. But as you can see, you have a gradual ramp up and a hold where it equilibrates, a ramp up and a hold where it equilibrates again, and then as it ramps up to its final and maximum temperature to cure, and then a cool down. So when using a foam substrates, we recommend that you always follow the manufacturer's recommendations on this portion of the curve. In other words, until you get to the end of the high temperature cure. And depending on what you desire for your foam afterwards is where we get into how to modify the cool down cycle. So in an oven, we have looked at a cure profile using the same profile, and all these lines on here are just different parts of the oven to show that it's all uniform temperature in that oven. So we have the same steps, the same maximum cure profile up here. Now, since the foam is so insulative, you can say embedded, just 2 to 3 inches below the surface of the foam, that it comes nowhere near the maximum temperature of that cure cycle. And some matrix resins will gel at temperatures below their maximum as well. And so that's where the CTE compensations come into play. Because the foam doesn't really grow at the same rate that the temperature ramp up is showing, we need to compensate for a lower CTE value to make sure that the calculations are correct if you don't overcompensate for the foam. So run that through again really quickly. As the temperature goes up, the graphite tool on top is really not expanding to any appreciable amount, but the foam will expand at a faster rate. So therefore, your graphite tool will gel and set shape at a higher temperature, which means the foam is larger than what was machined at room temperature. So you need to compensate for that difference in your tool design. And what we offer customers now is different temperature profiles. In other words, what temperature is the foam really at when a customer will provide what their ramp-up schedule is. Now, this type of profile is a very large tool would likely cause the tool to show surface cracks and potentially not be reusable or cause the need for patching afterwards. So for one-time prototype use, you want to get through your oven autoclaves quickly. You can cool it at the recommended rate for your graphite composite on top. But if you want to use the foam again, again we recommend some step down, which basically equilibrates the surface temperature of the foam with the inside of the foam to try to match the thermal expansion closer so that we don't get surface cracking and your foam can be reused again. What that does is it does extend the time of your cure cycle. So again, these are things to discuss with your supplier and also do some prototyping ahead of time. Now, I want to get into a case study where we actually used X-Tool M61 from Hexcel as a foam master. So 4718 is an excellent choice for the substrate for a lot of the previous slides description. It has a high TG, compressive modulus, and a predictable CTE. And the foam will not distort under the cure conditions. The X-Tool M61 tooling compound can be machined after post-cure to the final dimensions. So therefore, any anomalies in the foam growth over a complex shape can then be corrected for by your machining operation at the end. This is a photo of a consolidated but uncured hex tool with 4718 released with AirTech release film. And these photos and a lot of the process is taken right out of the hex tool user guide we've referenced below. So the overall process we're going to run through is looking at a 4718 billet, machine it down to its desired shape, we seal it, lay it up, cure it, post-cure it, and then we demold the product and build up a backing structure, and that will give you your finished tool. And we're going to focus more on these two steps in the middle here. So again, bonding and machining. So many different adhesives can be used, whether they're epoxies or urethanes or acrylics. But because the foam is so insulating, you want to use ambient cure adhesive. You don't want to have to heat the foam blocks up to cure the adhesive out, because that adds more time and cost by allowing your foam blocks to cool down before you can start machining them. And we also recommend to vacuum bag the final bond up before the glue has gelled, and that will allow you to consolidate and remove any air bubbles out of the glue and prevent really large bond lines. And after machining, you can see the bond lines in here. And this is a very easily machinable foam, and some type of dust removal, air hoses, vents, vacuums to remove off the dust as it's being machined. So we'll move into a little different shape tool, and the most proven and efficient method to release a foam tool of lower density, so lower density of course has higher surface porosity, is using a product from Airtech called Tool Tech, which is a fiberglass reinforced PTFE tape, and it has a pressure sensitive adhesive on it, and for example, a large 100 square foot surface area tool with 2 or 3 people working on it can be sealed up in about 15 minutes, versus a large tool like that with using a filler and sealer method would be a couple of days by the time you get it all sanded to your desired finish. The layup and thermocouple placement is really important as well. So typically on a metallic tool, you would have your thermocouple placement somewhere in the middle of your ply layups, because you'd be heating from both sides. On a foam tool, you want to have your lagging thermocouple between your foam surface and the composite lower ply of your composite, because again, you only be heating from the oven surface, which is above the tool, through the top of the graphite. So you want to make sure your second thermocouple, which is your leading thermocouple, is on top of the bag, and then make sure those two match up to show that you've cured the resin out as directed by the supplier. Now, you also want to make sure your thermocouple is at least 3 or 4 inches from the edge of your tool to prevent any kind of edge effects. Also, for larger tools, more thermocouples is recommended. Every 8 square feet you should have a pair of thermocouples monitoring cure, and we also recommend that they are placed near the airflow of your autoclave, for example, or oven. And again, there's some much more detailed practices on the layup, which I didn't go into here at all, from the supplier XL, and that link again is below. So the final steps, we look at bagging, curing, and now we're ready to debag the product and look at the results. And if we look at the before and after, even in an inert atmosphere autoclave, which of course is recommended in best practice for such large high temperatures and large amounts of organic material in the autoclave, we start out with a very cream colored material, and as we debag it, we reveal some oxidized foam surface. And within a couple millimeters below that surface, the foam is again back to its cream color, and it doesn't affect the properties. And we've taken foam through multiple cycles and have not seen any decay or surface degradation. However, it's with an inner atmosphere and properly vacuum bagged and sealed. So again, the demold the materials. This is the Graphite X tool. This is from the tooling surface. You can see the seams overlapping from the Tool Tech tape. And this is the resin-rich surface, and typically best results are seen when you remove that resin-rich surface and expose the fibers below there. And this product is recommended to be machined after cure. About 60 thou, material is removed to show this nice marbly finish that's been polished and is now ready for use. So again, just to review the overall process steps, we start with your foam master block. We NC machine it to its desired shape, and we apply the graphite after, of course, releasing it, recommending the Tool Tech. And then we have the backing structure built up after post-cure, and then your tool is ready to go. And this step here, if properly planned out, can be quite straightforward. So in summary, used from ambient to high temperatures and under different pressure conditions, FR4700 is a great solution for these higher temperature cure profiles. The blocks can be bonded to make large, complex shaped material. Another cost savings advantage to using to foam is you can cut your blocks to minimize the amount of material you have to machine off afterwards. But it is machinable in the rapid surface preparation using a released film instead of the filler and surface sealers. And also with the controlled cool down rates, we've shown that several tools can be made off of these parts. And again, a lot of that is very dependent upon your cure profile and cycle and complexity, complex shape of the tool. So if there are any questions, I think now's happy to field as many as you have out there. Thanks very much.
Great, thank you, Mitch. We do have a few questions. So I'll just run through those. I'll read them out loud for attendees, and then I'll let Mitch, if you want to answer them, you can. The first one is, you touched on the curing cycle. How do you determine the cure cycle? Is it density, size?
Yeah, and so every cure cycle, well, like I said before, the cure cycle is really, the front end of it is dominated by the fabric and resin supplier. If you're using resin infusion or if you're using prepregs, we really don't recommend ever deviating from those instructions to ensure your composite is cured out properly. But looking at compensation values, it's really a function of product density, thickness of cross sections, and then as well as dwell times at the different heat up steps, and then and also of course where your prepreg is going to gel. So those are all questions to have with the technical resources available from your suppliers. We're happy here to talk about those things. We have staff on hand to help with that.
Okay, next question. Do bonded sections of the HDU tool leave witness marks on the end item?
Potentially. What we do to minimize that, and what the question is referring to is once you have a bond in there, the bond adhesive is a higher density than the foam around it, and so under pressure, even in a vacuum bag only, the foam may compress just enough so you can see, as mentioned, the witness marks from the bond line. And what we do is we basically take an epoxy adhesive, and we'll fill it with either dust from our 4700, or we'll fill it with glass microspheres of very low density, like K1s or K15s from 3M, and we blend those together and use that as the adhesive, and that does help reduce the mark off of the bond lines. It's also one of the benefits of the hex tool and other products. But the one we've used the most is that hex tool, because it does you do machine your desired surface afterwards, so then those bond mark offs really don't show through. But for other polyurethane products that we offer and other companies offer, you want to match your adhesive to the similar density of your foam substrate.
All right, thank you. Next question is, what are the electrical properties of HDU?
That's a very good question, and we do get asked that frequently as well. We have different formulations, and we can also modify the connectivity with different additives. Foam is typically a pretty good insulator, but it's pretty formulation dependent, depending on what level of degree of detail you're interested in. So I'll take that one offline. If you want to email me that afterwards, we can address that one-on-one.
Okay, next question is, what is the compensation factor for your foam?
So that again goes back to what is the gelling point of your prepreg, and also cross-sectional thickness of the foam master you're looking at using, and putting those together. And what really can't supply a definitive answer to that because shapes and sizes of parts and tools always are always different. So that's something else that I'd be happy to discuss offline on a project basis.
Okay, next question. If you never have used soft tools before, what one factor is the most important before starting?
The biggest thing is to make sure you look at initially tech data sheets to ensure and get some samples to make sure that the parts you want to build are really going to be obtainable from the soft tools you're looking at using. Again, just all suppliers are really interested in helping make sure our customers are successful. So having that conversation via email or telephone, I think, is really, really encouraged.
Okay, I think we've come to the end of our questions. We did have a few questions about the availability of this presentation after the fact. This webinar will be available online after this presentation, and attendees will receive an email notification about accessing that. Other questions can be dealt directly with by General Plastics, and we do have all the questions and contact information. So, Mitch, you can follow up with these folks after as well. But that does bring us to the end of our presentation. I do want to thank you, Mitch, for talking to us today, and I want to thank all of our attendees for attending as well. We appreciate it, and have a good day. Thank you, Mitch.
Thank you, Ray.